Thank you for listening. This course was created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional podcasts, books, newsletters, and cool merchandise await. Let's get started. Model theft is the unauthorized acquisition or replication of a model's valuable assets, its learned parameters, architecture choices, training recipe, or deployment package in ways that deprive the owner of economic and intellectual property value. Unlike reading a paper and re-implementing ideas, theft copies the results of expensive learning without consent, shortcutting the compute, data collection, labeling, and engineering that created the artifact. The stolen value includes accuracy on niche tasks, robustness subtleties, and safety tuning that competitors cannot easily reverse engineer. Sometimes theft is direct exfiltrating checkpoints or container images. Sometimes it is indirect deriving enough of the model's behavior to stand up a convincing replica. In both cases, the owner loses differentiation and bargaining power. The threat is not only legal, it is strategic. A copied model erodes margins, collapses licensing opportunities, and weakens the incentives to invest in safer, more reliable systems that the whole ecosystem benefits from. Model extraction is a related but distinct attack in which an adversary reconstructs a functionally similar model by interacting with a deployed system. Instead of stealing files, the attacker learns the input-output mapping the owner exposes, probabilities, embeddings, or responses, and uses that information to approximate the decision boundary. With enough queries, cleverly chosen inputs, and iterative training, the attacker trains a surrogate that matches the victim's behavior on the domains that matter commercially. Extraction is often remote and stealthy. It rides the normal API surface, never touching the private network or storage. Because value lies in behavior, a high-fidelity surrogate can cannibalize customers even if its internals differ. The harm scales with granularity of outputs and query volume, rich confidences, and unrestricted access speed learning, while coarse answers and guardrails slow it. Either way, extraction converts operational exposure into a competitor's asset. Why steal or extract a model? First, to avoid the sunk costs of training, compute budgets, skilled staff time, and hard-won datasets that are expensive or impossible to assemble legitimately. Second, to gain commercial advantage. A replica can undercut prices or accelerate time to market by skipping research phases. Third, to bypass access restrictions. A gray market clone can provide features the original vendor limits by policy, geography, or compliance tier. Finally, theft enables further attacks. A surrogate is a sandbox for exploit development. Adversaries can study jailbreaks, prompt injections, or privacy leakage offline, then transfer successful tactics back to the target. In regulated sectors, extraction undermines fairness and safety assurances by divorcing behavior from governance. In all cases, the attacker converts your investment into their capability, while you retain the risk and the responsibility for incidents arising from your brand and deployment footprint. Cloud environments multiply the threat surface for model theft because convenience and scale invite subtle mistakes. Multi-tenant platforms share hardware accelerators. Weak isolation or noisy side channels can reveal timing patterns or memory residues. Misconfigured APIs expose administrative endpoints, verbose error messages, or debugging toggles that leak architecture and hyperparameters. Weak access policies over broad roles, long-lived tokens, or shared service accounts turn compromised credentials into keys for checkpoints and feature stores. Inadequate isolation between build, staging, and production allows artifacts to drift unencrypted through object stores or logs. Supply chain gaps matter too. Container registries, package mirrors, and model hubs become targets if signing and provenance checks are absent. Even observability can bite. If telemetry exports model internals, a monitoring breach becomes a model breach. In short, the cloud's strengths, automation, and reach also scale mistakes, so theft defenses must be engineered as first-class, least privilege defaults. Query-based extraction treats your API as an oracle and builds a dataset by design. The adversary issues adaptive, chosen queries that illuminate the boundary. For classifiers, they sweep the feature space to find where confidence flips. For language models, they craft prompt families that tease apart stylistic and content biases. For embeddings, they probe neighborhoods to map geometry. Collected inputs and outputs become supervised data for a surrogate, which is then trained, compared against the target, and improved with further probing. Over time, fidelity rises on commercially valuable regions, even if the surrogate remains weaker elsewhere. If your API returns probabilities or logits, gradient-free optimizers exploit those signals directly. If it returns texts, temperature and sampling artifacts leak style. Rate limits and random delays slow progress but rarely stop it outright. Persistent attackers orchestrate distributed clients and calendar-aware schedules to blend in with normal traffic while they learn. Parameter stealing aims to approximate or directly recover the victim's internal weights or sensitive intermediate values. In collaborative or loosely secured settings, gradients, optimizer states, or low-precision summaries can leak through logs, dashboards, or misconfigured endpoints. Side-channel observations cache behavior, kernel timing, or performance counters. Sometimes betray architecture details or even narrow ranges for parameters on specialized accelerators. Memory exposure is a perennial risk. Core dumps, crash reports, or leaked snapshots can contain tensors, embeddings, or tokenization artifacts that materially shorten cloning time. Adversaries are pragmatic. They combine partial leaks with public priors to constrain search spaces, then fine-tune a candidate until its behavior snaps into place. Even when exact recovery is infeasible, approximations reduce the effort needed for a high-fidelity surrogate. The defense lesson is simple. Anything that reflects training state is sensitive, and observability should never include raw model internals. Transfer learning turns a partial theft into a production clone. After training a surrogate that roughly imitates your model, the adversary fine-tunes it on public or cheaply scraped datasets that overlap your task, quickly closing quality gaps without touching your proprietary corpus. Because features learned by modern models are broadly reusable, a modest amount of targeted fine-tuning yields outsized gains. Classification heads align, styles converge, and idiosyncrasies of your prompts are absorbed. The attacker then ships a new model that behaves like yours where it matters commercially, while retaining many of your hidden weaknesses, jailbreak pathways, bias patterns, and brittleness near edge cases. In some cases, they even reuse your safety instruction style, giving customers the impression of parity. The result is rapid deployment of a convincing clone that captures demand and diverts feedback loops, all built atop stolen behavioral scaffolding rather than original research and rigorous safety validation. You can spot extraction in progress by studying behavior across sequences, not single calls. Attack traffic often shows excessive and unusual queries, grids of inputs that sweep parameters systematically, or long runs of near duplicates that probe decision boundaries with tiny perturbations. Patterns of adaptive testing emerge as prompts change in response to previous outputs, homing in on high-information regions. Distributional probing appears as disproportionate focus on rare classes, ambiguous inputs, or borderline confidence scores. Operationally, watch for sudden load spikes from new tenants, synchronized bursts across many IPs, and time-of-day clustering that mirrors automation schedules. Content signals matter too. Atypical token usage, entropy patterns, or requests that ignore product affordances in favor of raw probabilities. None of these signals prove theft alone, but together they raise confidence that someone is learning your function rather than using your product, justifying friction, investigation, and, if needed, containment. Hardening your interface raises the attacker's cost without unduly hurting ordinary users. Require strong authentication with short-lived per-tenant tokens and scope every key to specific endpoints and rate tiers. Enforce query quotas and burst controls so large adaptive campaigns must burn many identities, making coordination visible. Apply anomaly detection to traffic features request cadence, parameter diversity, input entropy, and trigger graduated responses when behavior drifts. Disable administrative or verbose modes in production and avoid exposing raw logits, gradient proxies, or internal IDs that supercharge extraction loops. Separate evaluation sandboxes from commercial endpoints and monitor cross-use. Finally, make abuse economically unattractive. Charge per token or per call at volumes where extraction becomes expensive, and reserve richer diagnostics for enterprise contracts with enforceable terms. The objective is not to stop every probe, but to ensure sustained learning attempts stand out from legitimate usage and face escalating friction. You can also reduce information content in each answer, limiting precision returning class labels instead of full probability vectors, coarsening scores into bands, or rounding to fixed decimals shrinks the gradient-like signals that attackers exploit. Adding controlled randomness such as calibrated noise to probabilities or randomized decoding among equally good answers breaks the repeatability needed for efficient optimization while preserving user-perceived quality. Caching common responses and delaying suspicious sequences by small variable intervals further impairs adaptive loops without punishing normal interaction. These techniques must be applied judiciously. Too much randomness confuses customers and undermines trust. Too little leaves extraction speed intact. Pilot changes with A/B tests focused on both utility and leakage metrics, and document the policy so developers know which endpoints return coarse outputs and why. Response modification is not secrecy. It is signal shaping to protect behavior from being harvested at scale. Strong cryptography keeps theft from becoming trivial. Encrypt checkpoints and optimizer states at rest using well-governed keys, and treat temporary artifacts, snapshots, cache files, debug dumps, with the same rigor as production waits. Ensure all API traffic uses modern transport layer security with mutual authentication where feasible, and prevent downgrade or plaintext fallbacks in internal paths. Secure storage backends with explicit bucket policies, object-level access controls, and replication rules that respect data residency. Practice disciplined key management. Rotate keys regularly. Isolate roles by least privilege. Monitor for anomalous use, and store material in hardware-backed modules rather than code repositories or environment variables. Remember that encryption is only as strong as its edges. Stage environments, build pipelines, and observability exports must avoid unencrypted spills. When cryptography is the default and exceptions are rare, opportunistic exfiltration becomes much harder and noisy enough to be detected. Logging and forensics turn suspicion into evidence you can act on. Instrument your APIs to record query metadata tenant, token, device fingerprint, timing, size, and minimal content features necessary for detection, such as hashed tokens or output entropy summaries. Track output anomalies, unusual probability shapes, repetitive phrasing, or spikes in near-duplicate responses. Maintain immutable, time-synchronized logs so you can replay sessions, reconstruct attacker strategies, and verify whether drift coincided with configuration changes. Link telemetry to attribution channels, signed client tokens, autonomous system numbers, and payment trails help identify coordinated campaigns behind rotating IPs. Preserve chain of custody for high-severity incidents so legal and contractual remedies remain available. Balance privacy by redacting sensitive fields and enforcing strict analyst access. Good logs support both real-time mitigation rate adjustments, CAPTCHA challenges, and post-incident learning that feeds back into hardened policies and better anomaly models. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Surrogate model detection aims to tell when another system has learned to mimic your model's behavior. One tactic is to watermark responses' subtle, statistically detectable patterns embedded in probabilities or phrasing that do not affect user utility but reveal provenance when aggregated over many calls. Another is to seed trap inputs, specially crafted prompts or feature combinations that cause your model to produce characteristic outputs. Replicas that learn from your interface tend to echo those signatures. Output fingerprinting goes further by modeling your system's quirks confusion between specific classes, temperature-dependent variation or latency entropy couplings, and checking suspect models for the same idiosyncrasies. None of these signals is definitive in isolation, so practitioners combine weak tests into a stronger inference. The goal is not courtroom certainty at the first sign, but a credible, evidence-based assessment that informs policy decisions. Notify a partner, rate limit a tenant, or escalate to legal and operational containment when thresholds are met. Legal protections convert your security posture into enforceable rights. Intellectual property frameworks provide some coverage copyright for code and text outputs, patents for novel methods, and database rights in certain jurisdictions. But learned parameters often sit in gray zones. Contracts are stronger levers. Clear license terms, acceptable use policies, and audit clauses create obligations for customers and partners, making extraction or reverse engineering a breach, even when technical lines are fuzzy. Trade secret law applies when you take reasonable measures to keep models and training recipes confidential. Rigorous access controls, logging, and need-to-know policies help prove that status. When disputes arise, you will need evidence. Provenance records, watermark statistics, and session replays that show systematic harvesting beyond normal use. The aim is deterrence through clarity. Publish terms, educate customers, and reserve the right to suspend service paired with a litigation-ready dossier that turns technical harm into recognizable, enforceable claims. The economics of theft ripple far beyond a single lost contract. A high-fidelity clone erodes revenue by offering similar performance without your development costs, forcing you into price competition just as margins should be paying back research investments. Competitive disadvantage compounds when the cloner underinvests in safety or compliance. Lower costs let them move faster, attracting users who are indifferent to risk while you shoulder the expense of responsible practices. Innovation suffers as return on investment shrinks. Teams redirect effort from frontier work to defensive engineering or cost control. Ironically, theft can increase industry risk appetite. Once clones proliferate, pressure rises to ship quickly and cut guardrails to keep pace. The feedback loop is corrosive differentiation, less incentive to invest, and a market flooded with lookalikes. Quantifying these effects for leadership clarifies why anti-extraction work is not overhead, but core to protecting product strategy and shareholder value. Side-channel risks remind us that behavior leaks through the edges of computation. Cache timing and memory access patterns can reveal aspects of architecture or workload characteristics on shared hardware, especially in multi-tenant accelerators. Power draw and electromagnetic emissions, while harder to exploit at cloud scale, have been used in lab settings to infer internal states, and they motivate careful configuration and isolation at high assurance levels. Memory dump exposure is more mundane but more common. Crash reports, core dumps, or orphaned snapshots can contain embeddings, token buffers, or partial weights ripe for reconstruction. Accelerator ecosystems add their own angles. Debug interfaces, DMA pathways, and vendor-specific telemetry must be locked down to prevent introspection. The practical lesson is twofold. Treat observability as potential exfiltration, and assume an adversary will chain small leaks with public knowledge. Hardening here reduces the chance that clever physics or sloppy debugging becomes a shortcut to your model. Governance integrates technical controls into how an organization makes and enforces decisions. Establish a policy that classifies models and artifacts by sensitivity, defines approved storage locations, and specifies who may access checkpoints, prompts, and datasets under what conditions. Require third-party audits, or at least attestations, for vendors that touch your training or serving pipelines, including managed labeling, hosting, or evaluation platforms. Codify incident escalation. What constitutes suspected extraction, who leads triage, when to notify legal and customers, and which levers rate limits, key revocation, model rotation, are authorized at each severity. Map these practices to your compliance regime so controls are visible in frameworks your auditors understand, whether service organization controls, international standards, or sector-specific rules. Governance should feel like paved roads, not barricades. Clear templates, default secure repositories, and automated checks make the right behavior the easy behavior, reducing reliance on heroics to keep models safe. Standards and benchmarks for model theft and extraction are early but evolving, and your program benefits from shaping them. Measurement begins with fidelity metrics that reflect commercial harm, agreement rates on high-value slices, calibration alignment, and transferability of jailbreaks from suspected surrogates to your system. Security groups publish guidance on API hardening, watermarking, and traffic analytics, yet mature, shared benchmarks remain sparse. In the absence of universal frameworks, develop internal evaluation criteria, red team playbooks for extraction attempts, acceptance thresholds for information content in responses, and procedures for rotating traps and watermarks. Participate in industry efforts to define taxonomies, datasets, and protocols so results are comparable across organizations. As the field matures, align to emerging profiles just as you would for encryption or incident response. Until then, treat benchmarking as a living artifact updated alongside product changes, so your defenses are measured, not merely asserted. Operational safeguards start with strong tenant isolation, the practice of separating customers, workflows, and environments so a mistake in one place cannot spill value into another. Isolate compute by assigning dedicated accelerator partitions or nodes, not just logical tags. Isolate networks with private subnets, strict egress policies, and service-to-service allow lists so model endpoints cannot casually reach storage or management planes. Isolate data by using per-tenant keys, buckets, and databases, with policy bindings that prevent cross-project reads even if credentials leak. Build test prod should be different universes, with artifact promotion occurring through signed, verified pipelines rather than ad hoc copies. Rotation and ephemerality help. Short-lived tokens, disposable environments, and immutable images reduce the chance that yesterday's credentials still matter tomorrow. When isolation is real, not merely a naming convention, an attacker must defeat multiple boundaries before a checkpoint or prompt library becomes reachable, transforming opportunistic theft into an expensive, noisy operation that your monitoring can catch. Continuous monitoring is the second pillar because theft and extraction are dynamic behaviors, not single events. Telemetry should cover identity and intent, who is calling and why, content characteristics, entropy, duplication, unusual parameter combinations, and system performance, latency patterns that hint at adaptive probing. Build detectors that watch sequences. Extraction campaigns rarely look like one-off spikes. They resemble methodical sweeps or staircase patterns of exploration. Couple detection with response playbooks that automatically raise friction challenge, slow or narrow outputs when confidence rises, and downgrade when behavior returns to baseline. Observe the model's own health. Shifts in output distributions, class confusions, or rare token rates can indicate that a surrogate is siphoning high-value regions. Finally, monitor your supply chain. Registry access, model hub interactions, and build system signatures are often where direct theft begins. Monitoring is not about catching everything. It is about noticing early enough to force attackers into mistakes. Layered authentication makes every privileged action earn its keep. Public traffic should meet strong, modern requirements, mutual transport layer security, where practical, short-lived OAuth tokens with tightly scoped claims and device or workload identity that binds calls to specific runtimes. Administrative and artifact operations deserve step-up controls, phishing-resistant multi-factor using hardware keys, just-in-time elevation with time-boxed approvals, and session recording for high-risk consoles. Service accounts must be narrow, per environment, per purpose credentials rotated by automation, never shared across teams or embedded in code. For machine-to-machine paths, prefer workload identity federation over long-lived secrets, and enforce policy at the edge with identity-aware proxies that understand routes and methods. The goal is to limit blast radius, Even if a developer laptop is compromised or an integration token leaks, the attacker cannot reach model checkpoints, DevOps scripts, or internal dashboards without tripping additional gates that your monitoring and forensics can trace. Regular risk reviews prevent drift from eroding your defenses. Schedule architectural reviews that revisit threat models as products evolve, paying special attention to new endpoints, richer outputs, or expanded partner access that change extraction economics. Run red team exercises focused on query-based learning and parameter exposure, and treat findings as backlog items with owners and deadlines. Include incident rehearsal, tabletops that walk through suspected extraction, the thresholds for action, and the legal and customer communication paths that follow. Reassess vendor posture hosting, labeling, managed feature stores, with evidence of isolation, key management, and audit trails. Tie results to metrics. Key risk indicators like percentage of endpoints returning probabilities, average token lifetime, or unencrypted artifact count concentrate attention on what moves the needle. Reviews are not performance theater. They are pit stops where teams refuel, change tires, and rejoin the race with a car that can finish. Model theft and extraction are best understood as economic crimes executed through technical means. We explored how adversaries either exfiltrate your artifacts directly or, more subtly, reconstruct your behavior by querying your interface and training surrogates. Motivations are straightforward: saving training costs, skipping restrictions, and building a platform for further attacks, while cloud realities compound risk through misconfiguration, weak isolation, and side channels. The visible signs are behavioral: adaptive sweeps, boundary probes, and unusual entropy patterns that stand out over time. Each of these pressures, your differentiation, your pricing power, and your willingness to invest in safety. Treat the threat as you would fraud or abuse: persistent, creative, and responsive to your controls. Success depends on clarifying what you must protect: the behavior, the weights, or both, and setting policies and telemetry that make sustained learning look and feel expensive. Defenses work when they change incentives. API hardening, response modification, strong cryptography, and rigorous logging raise the cost of extraction. Watermarking, trap inputs, and output fingerprinting raise the probability of detection and legal remedy. Governance, standards, and operational safeguards translate intent into everyday engineering choices. None is sufficient alone, but together they turn theft into a visible, risky project rather than a quiet background activity. As you continue, the next topic, adversarial evasion, shifts from stealing value to distorting decisions, showing how inputs can be crafted to fool models without copying them. Understanding theft prepares you for evasion because both exploit edges in how models learn and how systems expose that learning. The through line remains the same: build for measurement, layer defenses, and align teams, so protecting model value is everyone's job, not a last-minute patch when a clever replica appears in the wild. Thanks for tuning in to Bare Metal Cyber, your trusted source for cybersecurity educational materials, news, and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.